13th International Physics Olympiad year 1962 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com or Skype name Eduard F. 1996. Problem number 3. Hot air balloon. Consider a hot air balloon with a fixed volume VB equal 1.1 cubic meters. The mass of the balloon envelope, whose volume is to be neglected in comparison to VB, is mH equal 0.187 kg. The balloon shall be started where the external air temperature is Theta1 equal 20 degrees Celsius and the normal external air pressure is P0 equal 1.013 multiplied by 10 power 5 Pascal. Under these conditions, the density of air is ρ1 equal 1.2 kg per cubic meter. Question A. What temperature Theta2 must the warm air inside the balloon have to make the balloon just float? Question B. First, the balloon is held fast to the ground and the internal air is heated to a steady state temperature of Theta3 equal 110 degrees Celsius. The balloon is fastened with a rope. Calculate the force on the rope. Question C. Consider the balloon being tied up at the bottom. The density of the internal air stays constant, with the steady state temperature Theta3 equal 110 degrees Celsius. Of the internal air, the balloon rises in an isothermal atmosphere of 20 degrees Celsius and the ground pressure of 1.013 multiplied by 10 power 5 Pascal. Which height h can be gained by the balloon under these conditions? Question D. At the height h, the balloon, question C, is pulled out of its equilibrium position by 10 meters and then is released again. Find out by qualitative reasoning what kind of motion it is going to perform. Solution for problem number 3. Hot air balloon. Question A. What temperature Theta2 must warm air inside the balloon have to make the balloon just float? Solution. Floating condition. The float mass of the balloon, consisting of the mass of the envelope mH and the mass of the air quantity of temperature Theta0, must equal the mass of the displaced air quantity with the temperature Theta1 equal 20 degrees Celsius. So it means that VB multiplied by ρ2 plus mH equal VB multiplied by ρ1. And from here we can find what is the density of the air inside the balloon. That will be ρ1 minus mH over VB, which is 1.03 kg per cubic meter. Then the temperature may be obtained from proportion ρ1 over ρ2 equal T2 over T1. And from here we can find that T2 equal 341 68.53 Kelvin or 68.38 degrees Celsius. That was a solution for question A. Question B. First, the balloon is held fast to the ground and the internal air is heated to a steady state temperature of theta 3 equal 110 degrees Celsius. The balloon is fastened with a rope. Calculate the force on the rope. Solution. The force Fb acting on the rope is the difference between the buoyant force Fa and the weight force Fg. So we have Fb equal Vb multiplied by ρ1g minus Vb multiplied by ρ3 plus mh and multiplied by g. Again, it follows with ρ3 multiplied by T3 equal ρ1 multiplied by T1. From here we can find that ρ3 must be equal to ρ1 multiplied by T1 over T3, which is about 0.918 kilogram per cubic meter. So from here we can calculate what is Fb. That will be this expression, and after putting numbers we will get 1.21 Newton. That was solution for question B. Question C. Consider the balloon being tied up at the bottom. The density of the internal air stays constant, with a steady state temperature theta 3 equal 110 degrees Celsius of the internal air. The balloon rises in an isothermal atmosphere of 20 degrees Celsius and the ground pressure of 1.013 multiplied by 10 power 5 Pascal, which height h can be gained by the balloon under this condition. Solution. The balloon rises to the height h, where the density of the external air ρh has the same value as the effective density ρ effective, which is evaluated from the mass of the air of temperature theta 3 equal 110 degrees Celsius inside the balloon and the mass of the envelope mh. So we have ρ effective equal ρ3 multiplied Vb plus mh over Vb, which is 1.088 kilogram per cubic meter. Now let's estimate what is the density of the external air ρh. That will be regular density in atmosphere, which is ρ1 multiplied by exponent power negative ρ1 gh over P0. Resolving equation 5 for h, we have h equal P0 over ρ1g multiplied by natural logarithm ρ1 over ρ effective, which is 843 meters. That was solution for question C. Question D. At the height h, the balloon from question C is pulled out of its equilibrium position by 10 meters and then is released again. Find out by qualitative reasoning what kind of motion it is going to perform. Solution. For small height difference 10 meters in comparison to 843 meters, the exponential pressure drop or density drop respectively with the height can be approximated by a linear function of height. Therefore, the driving force is proportional to the elongation out of the equilibrium position. This is the condition in which harmonic oscillations result, which of course are damped by the air resistance. That was solution for question D, and here we finished discussion for problem number 3.